two-dimensional atomic imaging laboratory from Professor Yong-Soo Yang groups as my supervisor and Hye Sung-jo as my teaching assistant. So basically I will going to present what I learned about reconstructing the FEPT volume using simulated FEPT atom structure. And this is the outline for today's presentation, and moving on to the first section is introduction about atomic electron tomography or AET. So basically using the transmission electron microscopy, we are hitting the sample with electron beam from many angles, and the projection will be detected by the ADF detector, and we can obtain the projection from many angles that we call the tiltaries in the B picture. And from the tiltaries, we can doing some computational mechanism using generalized Fourier iterative reconstruction or GenFire. So basically we are Fourier transform the projection series into the Fourier slice, and we put the Fourier slice into the Fourier grid, but due to the misinformation, due to the limited projection, there are several arbitrary number in the grid, and we can try to inverse Fourier transform to get the 3D volume reconstruction. But we can see because of those arbitrary number, there are several artifacts, and we can apply real space constraints such as positivity or any atom information, and we can get the 3D volume that is more clean. And we can do the Fourier transform again to obtain the newly updated Fourier slice, and we can use the measured data, which the tilt series Fourier slice to be the Fourier space constraint, and then we can get the combination of those two, and we can repeat this iteration until both the real space and Fourier space constraint is satisfied. And this is the method that I will use to reconstruct the atom of the FEPT nanoparticle. So I start with generate the simulated atom structure, and then build the original 3D volume. And then I try to generate the projection to obtain the tilt series from any angles, and then I try to do the adjustment for the misalignment to get a greater 3D reconstruction. And then we can apply this GenFire algorithm to the tilt series to obtain the 3D volume. And after we have the 3D volume that we have reconstruct, we do the atom tracing to find each atom position, the coordinate position, and we can classify which atom is the Fe and which atom is the Pt. So the first step is generating the projection. So from the MATLAB script that is provided by the tutorial page in Professor Yong-Soo Yang's lab, I simulated the L10 ordered FEPT nanoparticle atomic structure and tried to reconstruct the 3D volume of the nanoparticle. And then I tried to generate the two-dimensional projections using one of these three methods, the FFT, DFT, and I tried to rotating the 3D volume that we have reconstruct and summing along one direction, and in this presentation I will call it as sum. And we can make the tilt series for many angles. In this case, I made the angle from minus 70 degree to 70 degree with a 10 degree interval. And this is the result of the volume reconstruction of the FEPT. And basically in this simulation of the reconstruction of the 3D volume, we have several control parameters that we can set. So the first one is the debut Wöhler factor, which represent how the atom is vibrating due to the temperature. And we can see the left one is when the B factor is low, so it has less special probability for the atom to be there. But in this, it is more dense, and the atom might vibrating possibility of the vibrating is bigger. And then we can also set the atom intensity height, which represent how intense the atom will be visible on the reconstruction. So this is the lower height, and this is the higher for the Fe, for the lower Z. And we can also set the pixel size and angstrom. So the left side is the lower number of the pixel size. We can see it's more cubic, and the bigger pixel size, it has more spherical like reconstruction structure. And after I obtain the 3D volume, I try to generate the tilt series, and using one of those three, the FFT and DFT and the sum. And after obtaining the tilt series, I try to run the Genfire algorithm on that. And basically in Genfire we can use like two methods also to reconstruct the volume. We can use the FFT and DFT, but we can see the difference here. The FFT it has more artifacts around here, and the DFT is like cleaner, and we can see the atom more bright and more visible in the DFT. And from this data, I conclude that DFT result for Genfire is better than the FFT. And yeah. So after doing the generating projection using those three methods, I choose to use the DFT method, and I obtain this tilt series projection from minus 70 degree to 70 degree. We can see it's rotating along the x-axis. But actually in the experiment, the tilt series could contain several problems such as spatial and angular misalignment that might occur due to the holder device inability to reach the accurate angle. And it also experienced the pulsar noise that occur due to the discrete nature of the electron, the beam. Hence, we have some information that cannot be retrieved from the microscopy process. And it also experienced the Gaussian noise that happened due to the electrical device noises. And we can see from this problem, we can the object is like moving in x and y direction, and it's tilting in random angle, and it has noises. So in order to get a better reconstruction, we need to adjust those misalignment using the center of mass alignment. Basically, we are making the center of mass to be the new origin for each image to align the direction that is perpendicular to the tilt axis. In this case, the tilt axis is the x, so it will adjust in the y direction. And we also use the common line alignment. What is common line? So in the 2D projection that we have obtained, if we project it to one of the axes, we could get the one projected curves that overlap each other if the tilt series is tilting on the same axis. So basically, to obtain that, we are going to align all those 1D projected curves to overlap each other to achieve the alignment that along the tilt axis, which is the x-axis. So I tried this method for several conditions. The first condition is the spatial plus angular misalignment plus the noise. So this is before the alignment. We can see it's shifting in x and y direction, and etc. So after the aligned projection, it relatively stayed in the center, but still have like tilting in random angle, and it has noise. And we can also see from the common lines, it's not overlapping each other. So from this data, I conclude that these two methods, they cannot solve the angular misalignment, and we need other way to solve that. And the second condition is the spatial misalignment plus the noise. So I remove the angular misalignment, and we can get the common line is better than before, but due to the noises, they still have like not overlapping region on the curves. And from this data, I can conclude that to gain the great adjustment, we need to remove the noise. And I tried for the third condition, which was the spatial misalignment only, and we can get more cleaner. We can see the object is staying in the center, and it's moving along the x-axis, and the common lines is also almost perfect. We overlap each other. And from those tilt series, we can try to reconstruct the 3D volume using Genfire algorithm that I have explained in the introduction section. And we can see this is the 3D atom volume from the Genfire. It still contains such artifacts. And we need to apply masking, which was the binary mask, to exclude the artifacts. So how it works is we multiply the volume region with 1, and we multiplies the other with 0. Hence, we will only return the atom volume after masking. And after we obtain the 3D atom reconstructed volume, we are trying to trace the atom to find each atom coordinate position. So basically, the algorithm is iteratively searching for peaks, and we are going to apply the 3D Gaussian fitting to distinct the atom. So there are several parameters such as threshold, which represent the minimum peak intensity that we can consider as an atom. So any peaks that's lower than those threshold, we can just throw them and consider as a non-atom. And then there are also minimum distance, which represent the minimum distance between two peaks or other that can be considered to be a distinct atom. So any peaks that has less distance than this value, we can just integrate them with other peaks or just throw them. And then there's also maximum number of peaks, which represent the number of peaks we can trace in this algorithm. And this I compare the tracing result between the ideal volume and the simulation volume. There are several differences that we can see better after the atom classification. So after we know the atom coordinate position, we can classify them by the K-mean clustering algorithm. So we are going to comparing the trace peaks, and we are going to group them based on their similar intensity. So for the ideal atom classification result, this is the result, and this is the algorithm. So we are going to group the intensity. So PT has larger Z than the FE, hence the intensity will be larger. And we can see this larger intensity is the PT group, and this is the FE group. As we can see also, as we also can see in the right picture. And this is the simulation atom classification result. Yeah, it has some difference with the previous one, and this is the result, the PT group and the FE group. And from this simulation, we obtained the number of PT is 179 atoms, and for the PT is 249 atoms. And this is the comparison between the ideal and simulation. As I said before, there are several differences that might occur due to the low oversampling ratio value in the Genfire. So we can set the oversampling ratio value. If we set it too low, there are several information that is missing that we cannot retrieve by the Genfire algorithm. So if we increase the oversampling, it might get a better reconstruction. And also it might occur due to the tilt angle interval is too large. So I use like 10-degree interval. Because of that, the atom information might be not accurate as if we set the interval like smaller, like 1 degree, it would obtain a greater atomic information. So yeah, if we increase the oversampling ratio and decrease the tilt angle interval, we will obtain the better simulation of this FEKT nanoparticle volume. And yeah, this is basically what I have learned during my internship in multidimensional atomic imaging lab. And thank you for your attention. Let me say my grateful and thankful for my supervisor, Professor Yong Soo-young, and my teaching assistant, Hye Sung-jo, and the lab member that have helped me a lot in doing my internship. So yeah, that's all from me. Thank you very much.
So, do you have the questions from the audience? Yeah.
So you can see it single atoms. Those were single atoms. This is an amazing accomplishment, right? Um, uh, do you see lattice imperfections? Do you have an example where an atom is missing from a particular space?
Yeah. So here see that the data that I use for this simulation is basically simulated, and from the simulated data, it actually has some atom that is missing, not
Wonderful.
symmetrical.
Wonderful.
And unfortunately, if we increase the oversampling ratio, we might see the better resolution, the better constructed that more similar to the ideal, that we can see the missing atoms. But in my case, my oversampling is too low, because I cannot.
Thank you.
Thank you for the question.
I have a quick question. So you examine the crystalline nanoparticles, right? So and then you observe the misalignment based on the measured image. So here I have a question. If you have some the amorphous some nanoparticles, can you still do the similar method to adjust the misalignment in case if you have an amorphous nanoparticle?
Actually, I haven't taken a look at that kind of particles.
Maybe you can think about. Any other questions? Question, you're welcome. Please.
I have a question. I'm just curious about your introduction. You introduced some PPFFT first. Do you know what is different to the human FFT?
Can I confirm the question? So, is it this part?
Oh yeah. PPFFT.
Okay. PPFFT. So, actually, in doing the genfire algorithm, we are transforming the Fourier, the series to Fourier space. Hence, we get the Fourier slice. But in doing this algorithm, we need to do the interpolation, and due to the different coordinate of the Fourier space and the tilt series, we cannot do the interpolation so in order to be able to do the interpolation, we need to modify the space. Hence, we got the PPFFT that known as the pseudopolar fast Fourier transform. And in this space, basically, the tangent has the same value. So yeah, that's the difference between in Fourier space the theta is the same, but in this PPFT the tangent is the same. That's my
answer. Yeah. Okay. Then let's thank the camera. So let's move to the next presentation.